Okay, we have in section 2.1 looked at finding a tangent or a secant line through letting a floating point come closer and closer and closer to a fixed point. Then in section 2-2 we really looked at what it means for something to get very close to something else. That's our idea of a limit. And now we're going to just apply some simple limit laws, all right? So let me get that to happen here. Okay, there we go. These are the 5 limit laws. They are common sense, I think. If you look at them, they're exactly as you'd expect them to be. That if we're taking the limit of the sum of 2 functions, we can just break that apart and say it's equal to the limit of one function plus the limit of the other function. If we're looking at the difference of 2 functions, that I then can just take the difference of those 2 limits, all right? 3, this is really comes from 1. This almost shouldn't be its own separate law, because if I just had f of x plus f of x plus f of x plus f of x c number of times, I could write it as c times f of x. And then by just applying this law, I could break it all apart and then factor out the c. So this is really built on number 1. Then 4 is the product of 2 limits. The limit of a product of 2 functions is then going to be equal to the product of their separate limits. Just as you'd expect, the flip side of that same coin is that if I'm taking the quotient of 2 functions, if I'm taking the limit of the quotient of 2 functions, I can break them apart and take the limit of the numerator function and then the limit of the denominator function and then divide them. But there's one really important detail, and that is, of course, we don't like division by 0, so g of x cannot be equal to 0 when we plug in a. G of a cannot be equal to 0. All right? So just be aware of that. All right? So there are those 5 limit laws. Okay, I will get the next 6 limit laws here by magic. Okay, so there we have the next 6 limit laws. They're kind of common sense. I won't go through them now. You can read through them on your own. But it's worth pointing out that if you think about it, you can use 9. You can use 8 really to plug into 6 to get 9. All right. So a lot of these are just built on what you'd expect. All right. So we are going to do an example. So let's make that happen right here. So here's our example. What we're going to do is just use the limit laws to break this down and find the limit. All right. So remember those first 5, and I've got the next 6 here. You do not have to do this every time, but we're just doing it once really as a demonstration. That if you can remember, the 5th law says that if you have a quotient of 2 functions, that you can break them apart. So we can, in a sense, put this limit into the top and into the bottom. And then we can look at each one of these individually because we've got a difference and then a sum. And then we've broken that down. We've got a power here and a multiplier there. And also down here we've got a number multiplying by the x. So we can rewrite this then as the limit, again, as x is approaching -1 of x squared, and then minus the limit as x approaches -1 of 3x, and then plus the limit as x approaches -1 of 7, all over, and doing the same thing, limit as x approaches -1 of 2x, plus the limit as x approaches -1 of 1. Okay? So you could pause me and take a look at those laws there and the previous 5, and then list the numbers that go along according to which part of the breaking open of this rational function that we've got. But then you see that as we have a square here, we're just going to simply find the limit as x approaches -1 of x, and we're going to take that and square it, minus 3 times the limit as x approaches -1 of x, and then plus, well, we can maybe just jump out here where if we've got the limit of a constant, it is just that constant, so we can take that step right now because it's so convenient. Doing the same thing to the bottom, it's going to be 2 times the limit as x approaches -1 of x, plus the limit, let's also take care of that one because it's just the limit as x approaches -1 of 1. That is not a variable. Don't be tempted to plug in a -1 there. That's just going to be 1. All right. So no matter what x is doing, that is 1. No matter what x is approaching here, that is 7. So it's not going to change. Okay. So if I plug in -1 and then square it, I get 1. If I plug in -1 and multiply by -3, I get +3. These are all just sort of using these laws here. Again, I'll let you look for the number, interest of saving time, +7, and then all over, when I plug in -1 there, I get -1 times 2 is -2 plus 1. This gives me 1 plus 3 plus 7 is 11 over -1 equals -11. Okay? So, like I said, I will let you look through and attach the number of each step to the way I've broken it down, but that's the idea that you do. There's another good example in the book. Okay? Okay, well here I am to do 2 sample problems. I'm sorry, the first part of the video, everything was chopped off at the top, so I'm just refilming these 2 sample problems. The difficulty with these is that we can't use that direct substitution. I can't put in 0 to evaluate this limit as h approaches 0 because I get division by 0. So what I need to do is a little bit of algebraic trickery. I'm going to multiply this expression by the number 1, but in the form of a fraction, something over itself. And that something, when you see a radical, is going to be this exact radical expression, 1 plus h and 1, but opposite whatever that sign is. If that's a plus, this will be a minus, this is a minus, so that's a plus. And then this over itself exactly, 1 plus h plus 1, so that it equals 1. Then when I do the multiplying, I'm going to multiply the numerator and the denominator. Doesn't matter which I do first, but this is where the magic happens. A radical times a radical. The radicals go away, I get 1 plus h. When I do the inside and the outside bits, my rainbow, I get a negative radical and I get a positive radical, and they add up and they cancel, so they're gone. Then a -1 times a +1 is a -1. 1 minus 1, those cancel, and this just becomes h. All right. Down below, I have h times this denominator, radical 1 plus h plus 1. I can cancel these h's, and I end up just with a +1 for my h over that denominator. I can now, don't forget, sometimes it's easy to leave that off, that's h as it approaches 0. I can evaluate this limit now using the direct method by putting in 0. The square root of 1 is 1, 1 plus 1 is 2, 1 over 2 is 1/2. So this equals 1/2. The limit as h approaches 0 gets closer and closer and closer to 1/2. Check it on your calculator. Here we have one that's slightly different. We're going to rewrite this in the form of its fraction. Something to the -1 is the same as 1 over that thing plus h minus 1 over 3, whole thing over h. All right? Well, dividing by h is the same as multiplying by its reciprocal. So I'm going to just multiply it by 1 over h and get rid of all this. All right? So I'm going to do the math on this fraction, find a common denominator and add, and then multiply it by 1 over h. Again, just to review, I can't plug in 0 because I've got 0 there in the denominator. I'm going to rewrite this. I'm not doing anything to change it other than the way it's written so that I can use the direct substitution method. All right? Well, I'm going to multiply to find a common denominator by 3 across the top and across the bottom, and then I'll come back this way and multiply across the top and across the bottom. My limit then becomes 3 minus, when I multiply this by the top, 3 minus 3 plus h, all over my common denominator, which is 3 times 3 plus h. This whole thing times 1 over h gives me an h down in the denominator. Well, what happens here? I can distribute in the minus sign. Be careful to do that. And then 3 minus 3 is 0, and a minus h is left up above. So this just equals minus h. All right, that's my numerator. I can cancel that minus h with my h, and I now get a new limit, which I can use the direct substitution method in, and it is
negative 1. When I cancel the h's, I get that negative sign remaining, and then it's over 3 times 3 plus h. Well, when h becomes 0, it's negative 1 over 9, negative 1/9. All right? So there are your two solutions to two sample problems, very similar to page 115. Good luck. Okay, I'm back. And that's because I wanted to talk a little bit about the squeeze theorem in terms of a visual. All right? There are times when we have some crazy functions that might do something like this, where they oscillate and then they get smaller and smaller and smaller as they get close to 0, and then they get bigger and bigger and bigger like this. And we want to know what is the limit of this fluctuating function as it gets close to a particular point. In this case, it would be the origin. It might be somewhere else in a different situation. But in this case, what's happening to this as it gets closer and closer and closer to the origin? Well, if you zoom in on it with your zoom box and then enlarge it, it might look just more like this, but just as a fractal kind of a thing. We've just enlarged it and it looks the same, and you really can't see exactly what's going on. There's a technique that mathematicians have devised. It's called the squeeze theorem. And what it means is, if we can find a function like this, and then maybe a second function, we definitely need a second function. Sometimes it's a flat line or something, but sometimes it's a curve. And if we can show that these two functions each have a limit that approaches a particular value, in this case I haven't drawn it very well, but maybe as they get closer and closer and closer to the origin, these individual functions get closer and closer and closer to the origin, the red and the blue curve. So we can say, well, if we know that this blue line is getting closer and closer and closer to going right down to the origin, and we can say this red line is getting closer and closer and closer to going to the origin, and we know that this fluctuating one that's going up and down wildly is always trapped between the red and the blue, that it sort of gets squeezed down and pinched down, and it goes to that same exact limit. All right? So it's an easy way to deal with some of the trigonometric functions by squeezing them inside other functions we understand better. Thanks.